and this, yeah, this was one of the things that went bump, but in the daytime, unfortunately. So this session is, as Roger said already, things that go bump in the night. And the first speaker will be Thomas Goodey and Rene Verreault. And their topic is Review of Anomalous Physical Effects During Solar Eclipses and a Proposal for Coordinated Experiments During the Great American Solar Eclipse, 21 August 2017.
Thank you very much. Good evening, ladies and gentlemen. I am very happy to be able to speak to you after you have cheered yourselves up with a good dinner. Unfortunately, not everyone is back, but there you go. Many people have different plans for the Great American Eclipse, as you can see. All sorts of plans from all sorts of people. Anyway, I'll show you a map now of the eclipse as it comes up. This is the eclipse as it will cross America on the 21st of August next year. It comes in Oregon, and it comes along here. A little north of Colorado. You have to go to Wyoming or Nebraska to see it. And if you want to see the eclipse visually, this is the area you should best be in for best weather. Then it comes down along here, and it goes out in Carolina, in South Carolina here. And it'll take about 60 minutes to cross America. The duration at every point, at each point of totality along the center line will be approximately 2 minutes. And if you are towards the edge, it will be a bit less. If you want to enjoy the eclipse, you must see totality. It's absolutely hopeless not to see totality, which some people think is almost as good, but it isn't. Now, when you come to see a total solar eclipse, really, like most things in life, you get out of it what you put into it, what you bring to it. You see, the guys on the left haven't brought much. But the guy on the right here, this guy, has been doing homework. This guy may not have got himself quite ready yet. What I'm talking about here is a possibility for coordinated experiments in physics during the solar eclipse with the aim of finding anomalies in the behavior of delicate physical equipment. These have been persistently reported over more than 60 years, and the type of equipment that appears to have given results is gravimeters, torsion pendulums, or 2D pendulums, so-called spherical pendulums. These are pendulums of which you consider the motion in an ellipse. In other words, not just a straight line pendulum, but a pendulum that can develop an elliptical motion, which actually they all do. Now, speaking of gravimeter observations first, 3 times there have been clear observations of anomalies by people using old-fashioned Lacoste-Romberg gravimeters, which are mechanical gravimeters. There are several hundred of these in America, and I'm sure that many of you universities have access to departments of geology who may have access to or may own gravimeters. I'm sure that among all the people in this room, there are at least 10 gravimeters available for use. And the great advantage of doing an experiment with a gravimeter is it costs absolutely nothing. You just have to look at it or hook it up to the computer and record what it does. You don't even need a person to observe it. You better stay away from it, and it works automatically. The first observation of an anomaly was by a gentleman called Duval in Quebec in 1994, actually a colleague of my colleague Rene Verreault here. Here was the start of the eclipse. This is the reading of the gravimeter. It appeared the value of G appeared, and I say appeared, to get a little higher during the eclipse and to drop back to normal levels immediately after the eclipse. I'm sorry? I believe this is milligals. Microgals. Again, come and see us for details. We have not enough time to cover everything. Come and see us later for the details, because you'll find them very interesting. This is an observation published in Physical Review by a guy called Mishra in India, who was not on the central path of the eclipse. By the way, neither was Duval on the central path. You see, here's the value of G corrected for tidal effects. As you know, gravimeters are capable of seeing the Earth tides because they're very sensitive. You see this unexplained dip here, which is rather interesting, and you see a microgal along this line. The next one was an observation by a team led by a guy called Wang in China. Now, I mean, this observation really, it seems to me, almost incontrovertible. Here's the start of the eclipse. Here's the end of the eclipse. Shortly before the start, the values dropped here. Then they rose and were roughly as they should be during the eclipse. And then towards the end of the eclipse, it sort of came off. This looks like an edge effect. This gentleman was directly on the center line of the eclipse. So he was actually in an eclipse point in this area. And you see, actually, there's more effect just outside the eclipse here. on this side of the fourth contact. So this is it. I really, again, I don't see how this can be controverted easily, but you know, the world has ignored it. Okay, that is enough for gravimeters, and I strongly urge you, if you can get hold of a gravimeter, liaise with us. We will make suggestions, and you can do a very interesting experiment. Now, there have been claims of anomalous observations with atomic clocks and with torsion pendulums by Zhu in China, Saxon and Allen in America, and Pugach, who is in Ukraine. He's one of our colleagues. We're in touch with him. However, what I want to focus on now is anomalies in the behavior of delicate pendulums, sensitive pendulums, which Professor Verreault and I and our colleague Dimitri Olenici have been working on for a number of years. These are the chief anomalous effects that have been seen. I shall only describe the most clear ones. First, I'll talk about the observations that Professor Maurice Allais made in the 50s. He performed a series of marathon experiments using a so-called paraconical pendulum, which is a pendulum suspended on a little round ball so that it has 3 degrees of freedom. It can also rotate around a vertical axis. This is a poor photograph of his measurement circle with which he read the position of the pendulum, which is here. You can see that this is obviously made of brass. This is a pretty expensive piece of equipment, at least as expensive as a car. So that's it. Now, oops, pardon me. Now, this is a more general view of his equipment. Yeah, this is the chief of laboratory operating the pendulum. He conducted 6 series of 6 experimental series, each 1 month long, operating the pendulum 24 hours a day, releasing it, in other words, about 1,000 times, no, not 1,000, about 100 times during the day and night, with a team of 7 people. This was a pretty marathon thing to do, and the people had to be trained to read the movement of the pendulum, as well as simply release it. And that was not cheap, let me tell you. He claimed to observe systematic anomalies in the motion of the pendulum, nothing to do with eclipses, which he has attributed to an anisotropy of space. This is not consistent with physics as we know it, but anyway, that is his claim. However, in 1954, there was a partial eclipse in Paris. The line of totality was a good 800 miles away from where he was. And he didn't expect anything. It was a purely accidental observational, serendipitous, that during the eclipse, this is the track of the motion of the pendulum. You see? It's pretty brutal. And he had no idea that this was going to happen, but a purely accidental observation. Well, that's pretty interesting. And again, there's no clear explanation for why it would do that. To say it is a gravitational effect sort of begs the question, because it's not according to conventional theories of gravitation. It may be nothing to do with gravitation. It may be something else. Anyway, I became interested in this matter. So did Professor Olenici, and a chap called Mihaila in Bucharest. Professor Mihaila also became interested, quite independently, and we constructed various apparatus. Now, this is an interesting observation. I was in Portugal for an eclipse in 2005 with my apparatus. Professor Mihaila was in Bucharest with his apparatus, and Professor Olenici was in Suceava, northern Romania, for his apparatus. So these 3 graphs were taken for the same eclipse in late 2005 in widely separated positions. Now, although the movements are not particularly great in terms of the normal movements of the pendulum anyway, the variations, you will notice that all 3 graphs have a bottom, have a minimum around the time of the eclipse, which is rather interesting. I'm not putting this forward as definitive, but I consider it very suggestive. That's what we saw in 2005. Now, in 2008, we were operating in Eastern Europe, in a town in northern Romania called Suceava. I had this rather fine equipment built, which is a very solid tripod with a paraconical pendulum in it and a automatic recording system. I also, in parallel, operated a manual pendulum of the same dimensions and the same dimensions and specification, but in a different direction, in a different azimuthal orientation, in a separate room. And Professor Olenici operated a 19-meter-long pendulum in a extremely solid medieval clock tower, and 500 kilometers away from us, in Kiev, unknown to us at the time, Professor Pugach of the academy in Ukraine was operating several small torsion balances. So we were all operating together, but I and Olenici knew one another, but we didn't know the existence of Pugach at that time. Okay, what happened was, this is what Pugach saw on his torsion balances. There are several of them, you see, 1, 2, 3, 4, and they behave differently, but there was a certain jump in this one, and this one, not in that one. at the time of the eclipse, or somewhat after T max, you see, in the second part of the eclipse. Meanwhile, these are my results with my two pendulums. The automatic pendulum, which I was operating, this is the chart of how it behaved during the eclipse. And the manual pendulum, which I was working myself, did this. As you can see, these are pretty well synchronized with one another, these dips, and with a little lump jump in the middle. And they were after the end of the total eclipse, where we were, somewhat after. And now, but the real startler is what Professor Olenici saw, which is here. You see, this relates to the amount of precession of the pendulum in he did it every 7 minutes, in 35 minutes. This is a long pendulum, and therefore very stable. The longer the pendulum is, in general, the more stable is its behavior. And he had a 19-meter long pendulum. You see, this one at 11:15 UT relates to this line. The pendulum clearly precessed more than in all the other 35-minute runs. And I mean, again, I don't really see that this appears incontrovertible to me. I don't really see how anyone can argue that this is not due to some real physical effect. So those were Olenici's results. And put all together, the three of us, the other very noticeable thing is all three of us noticed the effects that we observed somewhat after the eclipse, displaced later than the central time of the eclipse. And for three of us to see this independently is mutually supportive. Okay, this is my conclusion at the time, and I maintain it now. I consider it an inescapable conclusion that after the end of the visible eclipse, as the moon left the sun, some influence exerted itself on our region containing our equipment, extending over a field of at least hundreds of kilometers in width. And I maintain this because I don't think, I'm not saying that even that it's an anomalous effect. I'm saying that there was some such effect, and I don't know what it was. Okay, now, Professor Verreault in Japan, along with myself, he took his equipment to Japan for an eclipse in Japan. I observed no anomaly at that time. He observed an anomaly, which it's not. You see, there's the Gaussian curve here. I don't completely understand this method of analysis, but he observed an anomaly during the actual eclipse of a greater precession, an addition to about 1/3 of what the normal Foucault effect is. Okay, now. Subsequent to that time, Professor Olenici has been building a specialized building in his place in northern Romania for housing pendulums. It's under construction here. You see, here's the pendulum tower sticking up from there, and the pendulum operating room is down here. The room is now completed. It's much bigger now, and it holds two. It's purely for operating pendulums. He has two long pendulums, about 6 meters long. So, now actually. I'll show you it in a moment. I'll now explain the construction of the pendulum which we have in the room over there, which you may see, and which is the pendulum we recommend people to use, or the pattern which we recommend during the eclipse next year. The suspension is absolutely foolproof. It has a 1 meter rod which bends to and fro. This suspension is due to Professor Verreault. We call it the Verreault cantilever suspension. It has the great advantage that it is absolutely foolproof and requires no maintenance. There's a wire hanging down from that, and I would recommend to have about 5 meters of wire. There's a bob of the Olenici style, which is lenticular and therefore is symmetrical and has the least possible air resistance. He invented this bob. And under that, there's an alidad, which means a device for determining azimuth, direction in space, which is my invention, consisting, it is an optical alidad with 4 light beams in an M configuration, and a little pointer on the bottom of the bob interrupts these light beams as it goes to and fro, and we take the timings from this, and some complex software, which again I wrote, determines the 4 important parameters of the pendulum motion: the period, the amplitude, the azimuth of the major axis of the ellipse of swinging, and the semi-minor axis of the ellipse, in other words, the eccentricity, which normally it gradually gets larger, but sometimes, anyway, it has complex patterns which we can determine. Okay, now, here is a video of the launch of our pendulum in Romania by Dimitri Olenici. Here it goes. This is the alidad. Consisting of, in this case, of 4 vernier photogates, which are, I think many of you will know what those are. They are available in many physics laboratories, and and the little point on the bottom of the pendulum, which you cannot see, interrupts the photogates and gives us 16 events in each complete cycle of the pendulum, 8 one way and then 8 the other way. On, off, on, off, on, off, on, off, one way, and then back again doing the same thing. And we collect hundreds and thousands of numbers from this, and that finally gives us the results. Okay, now I'm going to hand over to Professor Verreault, who's going to discuss the real physics. Okay, you just touch this one, Rene.
Okay, good night. Well, I have to hold this mic. If I get tired, then yell. Please. Okay, let's go now to some more physics on the pendulum. Well, I won't have time to go to the whole theory here, but the intention is to demonstrate that we have a rigorous scientific approach to the pendulum experiments. Before claiming anomalous behavior, one must know the precise classical physics behind the pendulum. The Foucault pendulum is generally presented in textbooks as an idealized 2D harmonic oscillator. But in fact, that system is much more complicated. It could be considered as a very low-speed gyroscope with highly nonlinear response, actually. Sorry, thank you. And okay. And then real pendulum are inherently anisotropic. That means that they have two different eigenfrequencies for different directions at 90 degrees. So the observed anomalies actually appear in the form of the time dependence of the orientation of those eigenaxes. This is a sample of period measurement to determine the eigenaxis, and then one see then the slow axis where there's a maximum period. By the way, the period precision is the 1 part in 1 million in our measurements here. Cameron Onus actually made his doctoral thesis on the Foucault pendulum, and he especially studied the anisotropy of the pendulum, and his equations finally suggest that the behavior can be modeled on a sphere. Actually, each elliptical orbit can be transferred to the geographical longitude and latitude of the sphere. So that actually then the equator contains the rectilinear oscillations, and the upper hemisphere is for left-handed ellipse, and the other one the other side. What happens then with this representation is that we can model the behavior with time of the pendulum as a circle in that sphere.
You're too modest, Rene. You've neglected to say that this new modelization is entirely due to you.
Yes, it's all right. Okay.
You have 2 minutes.
And if I use this model now back to the original data of Cameron Onus, then we see that these data actually fall on that circle. And in our own experiments, then we suggest that we experiment around the bottom part of that circle that we saw there. So that bottom azimuth actually is the slow axis azimuth, and the anomalies usually show up as a variation in time of that slow axis azimuth, so that we can just track it. Yeah.
The blue dots are actually the actual experimental data that we've received. The red line is a quadratic trend line, and you see how extremely accurate our pendulum is. Look how close the fitting is. It really surprised me myself. I'll carry on.
Okay, back then to...
Here's his reference. Now, I'll finish off. We've got 1 minute, okay. Now, if we can persuade some people, possibly you or friends of yours, to set up pendulums, it should not be thought of as a one-off experiment that can only be done during the solar eclipse, the upcoming eclipse. You can use it for a long time as a teaching aid. The physics of the pendulum, even without anomalies, is extremely interesting and important. There's some students looking at a pendulum. Furthermore, there are two more opportunities for you for very much the same thing. There's an annual eclipse crosses America in 2023, like that, and there's a total eclipse in 2024. You could even regard an experiment in 2017 as a rehearsal for these two. And basically, I think that this is a challenge to America to find out something new. And remember, the great advantage of organizing an experiment of this sort is that you don't have to be on the path of the eclipse. Anywhere in America, or even Canada or Mexico, experience a partial eclipse, and it will be the data will be equally valuable. As you see in the previous analyses, some of the effects were seen at the very end or the very beginning of the eclipse. In other words, when the moon was virtually just touching the sun in the sky. So don't think I'm out of the path, it's not worth it. If you live down there, or you live up here, or up here, wherever, such a result will be of extreme interest. And really, compared to the cost of other original physics experiments, the cost is absolutely minimal. Okay, thank you very much, gentlemen, ladies and gentlemen.
Thank you for the interesting presentation. Do we have questions?
So the main effect that you observed was a small change in the gravitational field, apparent gravitational field strength?
I wouldn't say that for the pendulum. For gravimeters, the only thing they can measure is the direction of gravity in the downward direction, and the variations are very small. With pendulums, the effects so far that have been seen have been manifested in a variation in the precession rate. Because, as you know, a Foucault pendulum precesses. As it swings to and fro, the direction of swinging gradually precesses clockwise in the northern hemisphere.
So there's really not much of an explanation at all for that?
Well,
or is there?
No. You see, this is an unexplained phenomenon. This is the point. And we want to have as many possible replications in America in 21st of August 2017 as possible. Because at the moment, some guy sees something in an eclipse. You've seen the type of thing. Okay, well, maybe he was drunk. Maybe he's lying. Who knows? But if you've got 6 or 7 people reporting anomalies correlated with the same eclipse, then such explanations can no longer be maintained.
Just one word, actually. This changes the anisotropy of the pendulum, actually.
Yeah.
That's the way it shows up.
That's how it manifests itself.
Now, how about the torsion pendulum? You mentioned it, but I don't think you actually...
Torsion pendulum, a large torsion pendulum, which, you twist it, and it kind of goes like that, and comes back, and comes back. The only thing in theory, the only thing you can observe, in prejudiced theory, the only thing you can observe is the period. And a variation of the period was noticed in 1970 by Saxel and Allen. However, actually, you see, the pendulum hangs down. It might possibly also act as a stationary pendulum. In other words, the direction of gravity might change slightly. And many torsion pendulums are not set up to show that. It depends on the instrumentation. A colleague of ours, Professor Kuusela of Finland, thinks he detected something like that in an eclipse in 1991 in Mexico. But he wasn't fully instrumented, you see. Any apparatus that somebody sets up should be instrumented so that all possible deviations can be monitored. However, I consider that it's very important to have several sets of standardized apparatus so that we can compare apples with apples.
Right. Thank you.
I have a question and a comment. So the question is, how large is the effect on the gravimeter? So that refer to the scale I could not read.
Several milligal. Quite clear. I'm sorry.
2 microgal.
Microgal. I keep saying that. Several microgal. Not very large, but quite clearly noticeable, as you can see from the...
So my comment is that unless you do a statistical analysis, you will not convince anyone. So I think you need a statistical analysis.
Yes, ideally we want several gravimeters, don't we?
Of the background.
Yes, but you see... Wait a minute. Let's go up here. Wait a minute. But for example, look at the Wang. That gravimeter was taking many, many, many readings. And then it's not just one reading, it's taking a reading every second or something like that. And there are a lot of readings. I agree that ideally there will be several gravimeters doing their job. And so that you can't just say, well, the gravimeter was broken, because it could be, you see.
Yeah, I'm just saying that, for example, for the gravimeter, you have to compare the data to what you see over one year. And then
yes, absolutely. We must
but do you have a number for that, like a significance of the effect? Do you have a number for that?
I haven't got the number, no. The Wang is pretty good, and I think it does have a number somewhere in it, the Wang report, which was in Physical Review. The Duval, I think he did some kind of analysis of that sort, didn't he? Sigma. Mishra's report is very fragmentary.
This is just my point. It's nice if you understand all the physics of your pendulum, but you need a good statistical...
Oh yes, certainly.
...analysis.
Certainly, and certainly duplication with several sets of equipment is extremely important.
So I want to say that first, I love your enthusiasm.
Well,
and
thank
your
you.
excitement
I'm not
for
a
this.
practiced speaker, but I'm trying to explain it all in the short time available.
And I also really love the idea of having a large-scale experiment with a lot of people involved to see
Yes,
if you're getting
and a
an
cheap one.
effect.
And a cheap one.
I was wondering, though, you know, a lot of times when people have so much enthusiasm and so much excitement, and they're expecting or looking for a specific outcome, experimenter effect comes into play. I'd wonder if you considered psychokinesis or PK might be affecting your pendulums.
This is something that we cannot exclude. However, perhaps the best way to exclude it, you see, very often the pendulums will not be in the eclipse track. They'll be off it, so there will be no great excitement by the event itself. And indeed, because we have the automated monitoring system, which is pretty accurate, the only thing needed is for the operator is that, say, every 40 minutes or something, he stops the pendulum, he brings it off to the side, he attaches it with a little cord, he steadies it, he waits for a couple of minutes for it to calm down, and then he burns the cord. So then he presses the right button on the computer to start up the recording again, and he presses the cord, you see. It's not very exciting. And he doesn't even really have to know when the eclipse is. And enormous quantities of numbers come flowing down the screen, but they mean nothing to him. Furthermore, we hope that in such an experiment, people will organize a small team, perhaps of students, to operate the pendulum for about 5 days over the eclipse non-stop. It's not very hard work, really. You know, you can do 6 hours of it standing on your head. So if you had like 4 people doing 6 hours, 6 hours, 6 hours, 6 hours, you could happily operate for 5 days, the day of the eclipse, 2 days before, the day of the eclipse, and the day after. And they don't really have to know much about the eclipse. They don't have to watch TV. So, the chance that they will see the eclipse is here now, it's not going to happen, because ideally you will try and keep them as divorced from the matter as possible. Ideally, housewives who have not the slightest interest in the eclipse would be the best possible operator. And
right. So by varying the experimenter, you can help to dissipate some
yes,
of the
yes, but in this situation we have absolutely no operator effect. Allais was plagued by operator effect in his operations, because reading the pendulum by taking sights with his sighting method and so on inevitably involves when you change the operator, the results change. But with our automatic Allais recording system, you couldn't fake it, because you get like 8,000 numbers for every 40 minutes. So you'd have to fake it. You'd need a huge system to just calculate fake numbers. So that's also an advantage of this system.
So compared to other things like the accelerometer in a cell phone or laser ring gyro, where does the pendulum fall in terms of sensitivity to the precession?
That's a very good question, because there have been 1 or 2 interesting results made effectively using microaccelerometers, the type that they put them on a chip now. And I could discuss that, but there's not time. And I would think I could also suggest experiments that could be done using that. However, the sensitivity of pendulum, well, it's hard to say. It depends exactly what you mean. Depends what type of effect you think is acting on the pendulum. But I would say...
you were talking about precession,
yes,
which is a laser ring gyro is also very sensitive to precession.
Oh, yes, but it is not a physical system in the same sense. It does not involve angular momentum and angular moment of inertia and so on. So I would rather stick as close as possible to equipment that has already been shown to observe anomalies. Well, I mean, other experiments will also be good, but it's a bit striking out in the dark. You can never repeat an eclipse. You only have one shot. You only have one shot at it.
Quiet him. Yeah, just add on the question. Actually, the precision of the gravitational constant, big G, is in 1 to 1,000 to 1 million. And our effects actually are in that order of magnitude.
Yes, I would say
the limit of Newton theory. You see.
Yes, I would say we're working in millionths, but not 100 millionths.
100th.
I would say we are not working in 10 to the minus 8, but we are certainly on the 10 to the minus 6 or 10 to the minus 7 level. This is only a very ballpark figure.
Yeah, and so we are at the fringe of the precision of gravitation. So this might be a gravitational effect, but it's not predicted by Newton. You see.
It's not predicted by Einstein.
Not Einstein. Einstein predicts something which are 1 part in 10 to the 18, but not that.
And I personally think that it's a new effect. If it exists, it's a new effect. And Whether it's gravitational or not is to some extent a linguistic question. In other words, do you intend to change the theory currently held of gravitation, subsume it under the same rubric? I would suggest that it might be more convenient for logical purposes to consider it under a different heading. But that when we know more about it, we'll be able to decide. I think what we need now is to see if we can get any results.
Thank you very much for your interesting talk, and thank you for the interesting questions, too.